All right, everybody, welcome. Glad you've hung in there to the second afternoon of Pi Ohio. I'm Brandon Rhodes. When I'm not writing Python APIs or writing Python applications, I'm wondering why the code in my APIs and applications is such a mess. The industry as a whole, I'm told that at the moment, the numbers are hard to find, that more software projects, even to this day, more projects fail than succeed worldwide in businesses and institutions. And as an industry, we're still explaining. We're still trying to learn why. A piece of that puzzle, I think, is the recent work that's been done in propounding the clean architecture, and I'm going to give some examples of how I believe that applies to Python. The inspiration for this talk is someone called Uncle Bob Martin, who is, he's really big in the Java and the strong object-oriented statically typed languages. And he recently, in 2011 and 12, was thinking about a new way of organizing his code, his applications, that he called the clean architecture. One of several ideas that came out at around the same time with about the same goal, but his became more popular because I think he drew a better picture. There was someone else that came out with something like called the hexagonal architecture, and it just wasn't as pretty. It didn't use colors. And so this is what people often talk about if they're going to refer to this idea we'll explore of putting I/O at the top level of your program instead of at the bottom. The pith, the center of the idea, this is not how he puts it, this is my spin on it. You're familiar with the idea of a subroutine, where your code can be running along and then make a call in Python, the two forms of subroutine, or the function and the method, where you can stop, invoke some other code, and wait for it to come back with an answer. The pith of the idea here is that we programmers have been spontaneously using subroutines backwards. For how long have programmers tended to use subroutines completely backwards, the wrong way? By my count, we have been doing it for 62 years, and my proof is that I went back and I found the 1952 ACM National Meeting paper in Pittsburgh, Pennsylvania. It was the second meeting of the ACM, but the first for which papers were published. And I found the use of subroutines in programs by Mr. D.J. Wheeler, Dr. D.J. Wheeler of Cambridge and Illinois universities. And you might wonder, am I really going to pull anything of relevance out of this guy's paper? Because it was a very different world. A typical computer at the time had about 1,000 words of RAM, could do about 1,000 operations per second, and required a dozen people to operate. Could programming a computer with 1,000 words of RAM really be anything like writing code in a modern language today? Well, here's just one example of something that you'll find familiar from this paper. How complex could programming even be with only 1K of memory? In the paper, he says, the preparation of a library subroutine requires a considerable amount of work. However, even after it has been coded and tested, there still remains the considerable task of writing a description so that people not acquainted with the interior coding can nevertheless use it easily. This last task may be the most difficult. You had 1,000 bytes in which to write your code, or I should say 1,000 words in which to write your code, and they still didn't want to document. So I think the world he was working in as I read this paper seemed very familiar, though in some ways very strange. He's advocating that instead of just having one huge piece of code in your 1,000 words of memory, you split it into routines that call one another, like instead of having a single function in your Python file having several. What does he advertise subroutines as being good at? Why would you organize code this way? He says that the primary reason is to hide complexity. All complexities should, if possible, be buried out of sight. And this, you see, is where everything went wrong. And he doomed us for the next several lifetimes of programming, because that then leads programmers to a quite natural mistake. I/O is always a mess. Trying to talk to a database, trying to parse JSON, trying to get things in and out of a file. It's a mess. It's often very idiosyncratic code that doesn't have a lot to do with the pure essence of what our program's trying to accomplish. And the characteristic error that we make is that we bury the I/O rather than cleanly and completely decoupling from it. In the time allotted for this talk, I'm only going to attempt one code example. So if we spend a second on this, it will get you set up for the rest of the listings in the talk. This is a simple function in Python that uses a now deprecated API on DuckDuckGo in order to look up the definition of a word. Builds a URL, in this case, uses the requests library. I was a good citizen. And I marked those two lines with, there's the I/O, there's that ugly complexity we'd like to make disappear. And then, having gotten the JSON data back, it can look and see if a definition was in fact returned for the word. The natural thing that we tend to do is say, well, I/O is kind of messy. Who knows tomorrow whether I might not be using some other library in order to do my HTTP. Who knows whether I might not have a different way to ask for definitions. For instance, if DuckDuckGo deprecates the API. Well, I guess that would invalidate all of it, so I'll stay with the example of what if the way that I do the I/O, what if the way that I make the HTTP request changes? We want to get that complexity and bury it, and so we make the fundamental mistake of the last 60 years. We get the I/O, pluck it out, and feel proud of ourselves from having done exactly what Dr. Wheeler said. We've hidden it in a subroutine. We have hidden the I/O, but have we really decoupled it? Pake Wheeler, I assert that hiding is not enough if you want to control the complexity of your programs. Here's the listing again, and I will just ask this. If you want to call find definition so that it doesn't really do any I/O, because you're testing it or because you've cached a result, just want to hand it the cached result instead of calling your lower level code, how do you do that? How do I call find definition without it actually doing I/O? And at least as the code is presented here, it's not possible. I have, you see, hidden the API. You don't see any API if you read find definition, but I'm still tightly coupled to it. The I/O is an inevitable consequence of calling find definition, whether it's visible in its code or not. I have hidden, but I've not cleanly decoupled. What if we did everything the other way around? What if when we saw a routine with I/O in it that's ugly and idiosyncratic and might change tomorrow, what if we rescued the logic instead of hiding the I/O? This is exactly the same lines of code, but in this case, I have pulled out the data operations and made them separate and left the I/O stranded at the top level of the program rather than leaving my logic there. And my claim is this, that listing 3 that we just looked at is an architectural success, while the others were architectural failures. Listing 3 shows in miniature what the clean architecture does for entire applications. Here's that top function from listing 3. the coupling between the logic and the I.O., the thing in my program that brings together logic and I.O. in a way that they both have to be called at once, is now isolated to a small procedure that mates my logic and my external I.O. operations together. It's very readable because instead of blocks of logic operations, I now have names for them. Build URL, pluck definition from this data, that document what each section of code was doing. The first listing had no documentation for what those series of operations did. This should remind you of a little bit of the extreme programming movement from the late 90s, early 2000s, where, remember, they said that if you ever see a piece of code with a comment at the top, that's a sign that you actually have what wants to be a function. And they would say, you know, if you're writing high-speed C code and you want it to run fast, mark it as inline static, but make it so it gets inlined at compile time, but semantically make it something separate. XP people actually believed it was a bug. This is why it was called extreme programming. They actually believed every comment was a bug, because every comment was knowledge that wasn't in your code. And if your code isn't explaining everything about what it's doing, to them it's bad code. So before you could commit in extreme programming, all the comments had to disappear, as in this case. We introduce a new name, a new identifier into the code, build URL that wasn't there before, so that semantic information about what do these three lines do becomes a part of our program's actual semantics. And in this, this maneuver we see is we turn pure logic into functions and thus have to give them names in the same way that XP did. We find that we're adding more semantic content to our code. So, our architecture in listing 1 was simply a procedure. A procedure meaning something that has side effects. You call it and some I.O. has happened when it's all done. Listing 2, the natural way of using a subroutine since the 1950s to hide complexity, resulted in hiding the I.O., but the top-level code there was still a procedure. All of our logic was stranded in a routine that did I.O. every time you called it. Listing 3, by doing the opposite maneuver, left the I.O. up in the procedure and resulted in pure functions. It resulted in downstream Python functions that don't do I.O., that don't have side effects. They simply take some arguments that are data and return some results that are just data. This has incredible ramifications, among other things, for testing. How would we have tested listing 1 or 2, where the goal is to not have your tests need the network and to talk to DuckDuckGo? Imagine that you want your tests to run on an airplane or at the airport, or you don't have Wi-Fi or something. 2 techniques have been developed over the 2000s in being pioneered, I believe, in Java and the other big OO statically typed languages. They are dependency injection and the idea of mocking, which in Python we can do through monkey patching without even modifying our code through something I'll show in a moment called mock.patch. Dependency injection was pioneered in 2004 by another of the big OO thinkers named Martin Fowler. His idea was to make the I.O. library or function that the routine needs to call itself a parameter. And this is really easy in Python. Functions in Python are first-class objects. You can pass them. Modules are first-class objects and can be an argument to a function. So instead of having find definition from listing 1, literally and always use the requests library, you could make that a parameter whose default, if it's not provided, is to use Knuth Wright's requests library, but which lets you substitute any other kind of module-looking object in instead if you want to skip the call out to DuckDuckGo. And here's how you might write a test against that function I just showed you. You'd make a fake requests library with a get call inside of it, just like the real requests library. But when it was asked for its JSON data, it can just return a constant. The test, therefore, can just set up a fake answer. We're not really doing any I/O here. We're just going to answer this fake JSON data back when the definition is asked for. And we can now call our code, find definition, and avoid any I/O by having it use our fake little requests library instead of the real one. So we get a self-contained test that doesn't actually spam DuckDuckGo with lots of requests and couple us to DuckDuckGo needing to be up and running and not having blocked our IP address yet because we're running so many tests. The problems with this are obvious. First, that fake requests library we wrote, well, it's not the real requests library, so who knows whether calling, the fact that we called it and got data back doesn't tell us that calling real DuckDuckGo will give us data back. It might look simple for one service, an I/O routine that just needs to make an HTTP request, but a procedure that also needs, let's say, database and file system access is going to need lots of injection. What you tend to get if you use dependency injection is high-level functions that need everything in the kitchen sink. Because if way down beneath them anyone tries to talk to the database, it's got to be dependency injected. If another procedure needs the web, it needs to be dependency injected. And this problem has actually spun up to the level of having huge dependency frameworks, dependency injection frameworks they're called, in the larger OO languages because of this problem of if the very bottom guy has got to talk to the web and you ever want to be able to test that code, then the top level procedure has somehow got to get the information about what the web is right now. Is it a test mock or is it the real thing when it's called? Now, a dynamic language like Python, fortunately, has ways around dependency injection, so we don't wind up with that problem I just described. Thanks to the mock library, incredible resource created by Michael Ford, we have the ability to live patch our I/O libraries to briefly substitute fake versions of their callables that will return the data we want. And I believe the mock library is now part of the most recent Python 3s. It's so important it was added to the standard library. In that case, we can use the original listing 1 or the original listing 2, and we can just ask the patch callable from the requests library to patch requests.get to be our fake version of it instead. Inside of the with statement, inside of this context, this block of code during which that patch is active, our test gets run, no real connection is made to the outside world, and we find out if our function works against purported data from DuckDuckGo. Whether you do dependency injection or whether you call mock.patch, I find that the result is kind of awkward and kind of sad. As I test, I just feel like I'm fighting the structure of my application. I feel like I'm trying to make it do something that it would really rather not do. So, how does testing improve? When we factor out our logic, as in listing 3, where we get the logic that simply deals with data structures and rescue it by putting it beneath the I/O rather than above it. Well, by definition, pure functions can be tested using only data. Arguments go in the top, a list or a string or some other data structure is going to come out the bottom. So for example, if I want to test the build URL, I just call it. I don't have to set up objects, I don't have to build things, I just call it with different arguments, and instead of going and hunting for side effects, I can just look at the return value and see whether it's what I expected. No special setup is needed. No special preparation. I don't have to build a mock. And the test calls I'm making look exactly like the calls that are used in production. So I know they have a high probability of telling me whether my code will work in production. Here, I'm going to test the second half of the logic, pluck definition, which needs to pull out the value of the definition key or raise an exception. 2 simple tests, and I have 100% test coverage of it. Again, making a pure call that is not in any way adulterated or changed or adjusted from the way this function will be experiencing reality when this code is in production. It's seeing exactly the same kind of things come in and go out as it will when I use it for real. Being able, by the way, to write the tests like that taught me about a symptom of coupling I had never observed, a symptom that tells me that I might have locked logic together that could be more cleanly split out. You'll note that all I had to do there was write one set of tests for building the URL and a completely different set of tests for whether I could parse the data that came back. And I noticed that in a lot of my older projects, I had bigger, more complicated routines where where doing the test for a good URL and good data was very easy to call, but that I then had to essentially start doing different permutations of argument to get each part of my logic to fail separately, because it wasn't out separate where I could call it. And so having a big series of pieces of logic where I want to make each part fail individually, I first have to make a bunch of calls with a bad URL, but that don't pass in a second piece of data because I never reach that part of the code. And then a series of tests that give a good URL so we survive the first half of the code, but then bad data so that that part will fail. And I now consider that pattern that I see a symptom, a cry for help, if you will, from my application code, telling me that I have coupled 2 pieces of logic together that are really separate. They do different things, they're going to fail in different circumstances, and that instead of leaving them coupled and then having to fiddle in turn each variable while leaving the others constant, I might be able to rescue these pieces of logic into separate functions. This does become, I do sometimes leave this pattern in my tests if there's just so much state shared between the first and the second piece of logic that it's just not reasonable to return all 20 things so that they can then be the arguments to the second piece of logic. This comes up a lot in astronomy, where an initial routine might set up a bunch of variables that the conclusion of the logic then needs to succeed or fail on before throwing them away and returning a simple value. But if you look at the output to the first piece of logic and find it's rather modest, rescuing the 2 pieces of logic out into separate routines can make your tests less expensive, simpler, and easy to think about by the fact that you're not getting big, tall sequences of logic and contorting yourself to try to get the third thing that happens to fail. All of which is invalidated, by the way, if you then change the order of your operations, because now you need something different to succeed in order to reach the second or third error or exception that could happen in your code. So that is a really, really simple example that we've just gone through, almost trivially simple. I made it only as complicated as I thought you needed to get the point. In real life, the clean architecture often involves much, much bigger pieces of code and the question of how they hook together, not 9-line functions and the fact that we can pull 1 or 2 pieces out. What Uncle Bob Martin does is as he's designing his entire application, he's thinking through what parts of my business logic can survive being split off, where they take arguments, take data structures, and return data structures, such that the top level glues all of these pieces together so that the I/O stays up at the top level, and the bottom levels are simply objects or functions that don't need to know where the data is coming from, where it's going, how it's getting persisted, but instead simply enforce your business rules, do your computation, and leave it up to the caller where to put the results. He says in one of those blog posts, in general, the further in you go in his architecture, the higher level the software becomes. The outer circles are mechanisms. The inner circles are policies. The important thing is that isolated, simple data structures are what is passed across the boundaries. When any of the external parts of the system become obsolete, like the database or the web framework, you replace those obsolete elements with a minimum of fuss. Because all the innards don't know about the database. The innards don't know that the web is there. And so if you need to replace the way your data is stored, the way data flows in or out, you just make adjustments at the outside level and everything else should keep working. Back to our code to make this concrete. We could change how we do the I/O. We could change how we batch up these operations. We could change what happens up at the top without having to change either of these functions down inside, because they take simple data as input, manipulate it, and return new data as output. All right, you might say, I would like to know whether my app works against DuckDuckGo. I do want to test my I/O code at least once, even if this pattern does let me do most of my testing with pure data. How do you test the top-level procedural glue? And here, I'd refer you to Gary Bernhardt's talks at PyCon 2011 through 2013, where he, from the Ruby world, that's his primary language, explored a different form of this same kind of approach, and talking about how to make the majority of your tests very fast and only investing in a few tests doing the end-to-end I/O-bound operations that there at the end tell you, yes, my app actually works and will actually fetch in real information from a database or whatever and work with it. His terminology is a little different than Uncle Bob's, but works in much the same way. An imperative shell at the top level that does I/O that wraps and uses your functional core. Functional core, because it takes and returns data, can have lots of fast unit tests, exercising directly all the ways it could fail, all the conditions it has to detect. Up at the top, your imperative shell hopefully only needs a few integration tests in order to verify for you that it works, because you're not having to hit the imperative shell with the 20 different ways that a word definition you're looking up could be misformed. You're doing that by testing the functional core. You just test the imperative shell to make sure the pieces are then hooked together correctly. Here's our top-level function from listing 3. I mean, there's not even any if statements here. It shouldn't require very many tests to confirm for you that this is doing the steps of your application in the right order. This pattern, by the way, is already familiar to a lot of people who do functional programming. Languages like Lisp, Haskell, Clojure, and F# make it quite natural to write most of your code as pure functions, and then you get awkward and put the procedural stuff up at the top. Functional languages naturally lead you to process data structures while avoiding side effect I/O. You tend to call functions in functional languages for what they return, not for the sequence of things they happen to do while that code is running. This is an example of I/O as a side effect. I'm getting a data processing task, iterating over a Python iterator to get a series of words and uppercasing them, with an I/O task. When you call uppercase words in this example, you're not expecting to see any uppercase words as its return value. You're expecting that when it returns nothing to you, it will have had a side effect in the outside world of producing those as output. If you want to test this, you're going to have to use mock.patch or something else to intercept the standard output. Here is an example of the same code split into a purely logical piece where it consumes an iterator that gives it words and produces as an iterator, as a generator in this case, a series of uppercase words, separately from the question of any side effects, And it can then be quite naturally plugged into a top-level, as Gary Bernhardt calls it, procedural glue routine, which then does the I/O on its behalf. Procedural code tends to be called, not because it's going to return anything interesting, but because of what it does, because of what it tosses out or pulls from the world. It tends to output as it runs. Functional code, on the other hand, tends to be organized in discrete stages that each produce data that then finally gets output at the end. In Gary Bernhardt's talks, he talks a lot about the immutability. A lot of these functional programming languages, imagine Python, where you didn't have lists, but only tuples. That once a list was built, you couldn't change it anymore. Imagine Python with dictionaries, that once you built them, you could never change them. Where if you wanted to produce a new dictionary, you had to ask for a copy of the old dictionary with like one thing changed or something. A lot of these functional languages have immutable data structures that never change. And some programmers who are fans of the functional programming style say that they're much, much easier if they pass a data structure to a function knowing it can't be changed, that they don't have to go search to see if it looks different, that every data structure is immutable. And they claim, some of them like to claim, that the whole point of this programming style is immutable data structures, so that you would feel guilty about having objects with writable attributes or dictionaries that you might update. And I'm going to make the argument that it is not immutability that makes the functional programming language so clean, or it's not the only thing. My guess is that the biggest advantage of data in a functional programming style isn't its immutability. It is simply the fact that it's data. And that data structures, you can see them, you can reason about them. Unlike a moving process that you're worried about whether it's spinning off consequences in the right order, a data structure is just something you can look at and understand. Two examples from computing history that I'll use to back me up on this. The famous Fred Brooks book, The Mythical Man Month, about successes and failures in managing projects, written in 1975. It's very famous. You've probably heard of it before because of the quote. This is back when if a project was going slowly, they would just keep throwing more developers in. The bearing of a child takes 9 months, no matter how many women are assigned. There are some processes that do not get faster because you flood the organization with with untrained people who don't know what's going on. And he often found projects, he's the famous aphorism that projects go more slowly the more people you add in many cases. He said the following on the question of what's easier to understand, data or code? At the time, code was usually written out as flowcharts, and data was usually organized in memory in what they call tables. He said, "Show me your flowchart and conceal your tables, and I shall continue to be mystified." Show me your tables? And I won't usually need your flowchart. It'll be obvious. Very often, if you just show someone the way that you've laid out your dictionaries and lists and other data structures, they can probably guess how you're going to run through those data structures and get your job done. There's something that's much clearer about seeing the data that you wind up producing or the data in an intermediate step than to stare at the steps in your program and try, starting there without any bigger picture of what they're creating, trying to guess or understand what result is being built or generated. So that's one example of a famous thinker in computer science who I think would back me up that the data is where it's at. But I'll also cite in the 1986 famous showdown between McElroy and Donald Knuth, who largely invented computer science in the 70s as he wrote The Art of Computer Programming. Knuth, very, very famous programmer, there he is, was asked to write a routine. He practiced something called literate programming, where he had lots and lots of comments, where a computer program could actually be published as a book explaining itself. And he was given by a programming magazine the task, given a text file and an integer k. Can you tell that computer science was invented by mathematicians? Print the k, most common words in the file, and the number of their occurrences in decreasing frequency. He produced 10 pages of Pascal code that did this. And McElroy said, he admitted, this is a formidable solution. Knuth's solution is to tally in an associative data structure, something like our Python dictionary, each word as it is read from the file. The data structure is a tree with 26-way, well, for technical reasons, actually 27-way, fan out at each letter. To avoid wasting space, all of the sparse 26-element arrays are cleverly interleaved in one common arena with hashing used to assign homes. 10 pages of Pascal. At the conclusion of his article, after reviewing Knuth's code, pointing out several bugs in it and edge cases that would make it crash, in one of the most famous moments in computer science, McElroy replaced Donald Knuth with a 6-line shell script. The first line finds every run of letters, A through Z or lowercase letter through Z, in the file and puts them together. It gets everything that's not a letter and turns it into a new line. Second command makes everything lowercase so that we don't count words twice if they're at the beginning and in the middle of a sentence. Sort is going to bring, all of the word instances of the word aardvark together in a row, and then all of the instances of the word Brandon and Python and so forth. Unique is going to get those runs of identical words, count them, and tell you 6 aardvarks, 5 Brandons, and so forth. I suppose I rate my popularity at slightly below that of the aardvark then. It is then going to sort that output on the numeric field sitting in front of each word, so that 6 aardvark goes first and 4 Python goes next, and so forth. And then finally, we ask sed for the first inlines and then quit. McElroy points out that every one of these tools, back as Unix was being invented, was written first for a particular need, but then untangled from the specific application. The person who first needed to put a sorter inside of their program got it written, and then stepped back and said, I'll bet someone else might need to sort something someday. And went to the work, which is difficult, of pulling that out so it could work on any text input file with any format. Now, the traditional lesson, and the one that McElroy drew here, was it's better to use simple, small tools that can be easily linked together. And I would say that if this is the only lesson we can draw from his showdown with Knuth, it's a very good one, because Python has lots of, because of the iterator protocol especially, it's really easy in Python to link together a series of generators, to throw in sets and lists and dictionaries at just the right point to get a lot of really interesting data processing done. But today I want to draw a different lesson that McElroy did not. To me, the shell script is simpler, not simply because the steps are easy, but because I can picture the data. It's because in between each of these pipes, in between each of these commands that data is flowing between, I can close my eyes and know exactly what that data looks like at each step. The shell script is the simpler solution because it operates through the stepwise transformation of data. And what's key here is not simply that the steps are easy to describe. I'll bet that many of you, even who didn't know the tr command before, could probably tomorrow explain this shell script to someone after a bit of head scratching. It's not just that the steps are easy, though they are. It's that I can just close my eyes and picture what the output looks like at the conclusion of each command running. And that's very powerful because it lets you visualize very accurately what this is doing. in a way that is not going to happen with 10 pages of dense Pascal that are producing an in-memory hash table 27-way fan-out binary tree. This approach continually surfaces intermediate results that can be checked, examined. If you find this doesn't work, you can just go back and find at which step it failed, in each case as simple plain text. So if I'm right that one of the big wins of a functional programming style is simply that it deals in data which our minds can picture very easily, what then is the value of immutability? And I think Gary Bernhardt got this right when he said the fun of immutability, I believe this was in the 2012 talk, is distributed computing. Is that, this is my only slide about this, is that if all of your routines just take a data structure and return a data structure, it doesn't much matter what core they run on in a big cluster. You can push data out to a bunch of servers, run the data steps separately, and then collect the output back. And a task that you've broken down into steps that simply pull in data and return data can then be hooked up to a message queue and fanned out across a very wide data server, so long as it's the return value that's important and not the side effect. If I call a routine and its value is that my data structure will now look different, it's got to live on the same machine, so it's changing the copy of the data structure I've got in memory. But if it's its return value that's important and not the way it monkeys with the data I already have in memory, it can run anywhere so long as the result is delivered. Data and transforms are easier to understand, and I think they're easier to maintain than coupled procedures. Now, if that's the case, Python has been evolving recently in exactly the right direction. If you think about the kind of innovations that have marked the last decade, especially in a decade and a half, as Python has grown from the language it was in the 1990s. In October 2000, we got the list comprehension. The list comprehension seems like a slight convenience, but it really changes you as a programmer. It takes someone whose job, our job, used to be modifying data structures, make an empty list and then go through and start changing it, and it turned us into people that build new data structures that we often never touch. Often my code today takes in a list and in a series of comprehensions, just like that shell script, generates a series of intermediate results and a final data structure that it returns without ever reaching back into one of the earlier results and feeling the need to change it. List comprehensions make it really easy to write Python code that's purely functional, where you're using write once, throw away data structures for your intermediate results, rather than doing constant modification. Python 2.4 saw the introduction of the sorted built-in. Remember how we used to sort? You used to have to build a list, give it a name, call its .sort method, which returns none, so you couldn't use it in the middle of an expression, and then go back to the list, which has now been modified, which is now changed, to see the result. Thanks to Raymond Hettinger's addition of the sorted built-in, we now just ask for data to be sorted and returned to us in a single step, instead of having to build and modify a data structure in several. And if you try applying these different patterns to your Python code, remember that Python has several different ways of breaking out a pattern from your code. We do have functions or methods, but remember that if it's iteration that you want to factor out, you can build a generator. If you have some setup and teardown that you want to pull out, you can build a context manager. There's actually, whereas older programming languages, let's say Java, will have one way to break out a subroutine, and then you have to come up with design patterns that fill in the lack of generators and the lack of context managers with something like the visitor pattern or something like that. Python just has all three of them built in. You can pull out the middle of a loop as a function. You can pull out the loop logic itself as a generator. You can pull out setup and teardown as a context manager, we have a lot of different ways of getting logic and doing that rescue operation where we decouple it from our I/O so that it can live separately. Two real-world examples, just current projects of mine, are Skyfield, an object-based API for astronomy backed by dozens of pure functions that were really easy to test. Functions implement the actual operations, and the miserable thing, by the way, about a method is that it implicitly depends on the state of the whole object. It's often hard to test a method because it's not clear how much of the object in the test needs to be set up and initialized before the method can run. Whereas the beautiful thing about a function is you just read the arguments and you know now what to provide to it. A well-written function doesn't need extra globals or other persistent state set up and available for it to run, which makes testing, bug fixing, a lot of easier. Remember, in the Zen of Python, which I hope you look at every morning as you get ready to code, second only in Python's motto behind beautiful is better than ugly is explicit is better than implicit. And a function, if nothing else, is very explicit about its needs. Right there in the argument list, tells you what it needs to succeed. So Skyfield is one example I've done recently that has turned out really well when I didn't strand my important logic up coupled into my objects or I/O, but where I spun off everything I could in an easy-to-call function. The other is something I use for filling in tax forms for myself called Lucha. It's also on GitHub. The temptation there, and actually the first version of it, as it ran along computing fields, would immediately then call the low-level PDF operations to, write them onto the 1040 tax form or whatever. I then was able to rescue that deeply, deeply compromised and very difficult to maintain code by breaking it into phases. I first read in the entire input of the tax form while resisting the temptation to do anything with it. I simply read it into a data structure and return that. I then have a routine that takes the inputs to a tax form, and it's very easy to write these little routines. Add up the numbers, do the rounding, multiply the percents, and produce all of the output lines in the tax form. And I resist the temptation to write that out to the PDF. I hand that data structure then to my PDF writer, whose only job is to fill text into fields. It was much easier to write and maintain code that was split so that data structures pass between phases, rather than making a slightly shorter program that immediately tried to go have side effects, but thereby made itself very difficult to test. So the pith of the idea here is that in the old days, if we wanted to get rid of all of that pesky I/O, we would try to accomplish that by turning it into a subroutine. The new idea I'm propounding is that if you really want to get rid of someone, make them a manager. Put them in charge. Get all of that I/O-laden code and make it feel important by putting it up at the top of your program. Make it the procedural glue, leaving all of the little function subordinates free to do their jobs. Let's return to Wheeler. I have one last quote. In 1952, he gave us the subroutine. And I think because of that initial phase of computing history in which we tried to use it wrongly, we have yet to realize its full power and promise. But I'd like to end with a quote in which he described what he thought would someday happen now that we have subroutines. He said, "When a program has been made from a set of subroutines, the breakdown of the code is more complete than it otherwise would be. This allows the coder to concentrate on one section of the program at a time without the overall detailed program continually intruding. Thus, the subroutines can be more easily coded and be tested in isolation from the rest of the program. When the entire program has to be tested, it is with the foreknowledge that the incidence of mistakes in the subroutine is 0. Or at least one order of magnitude below that of the untested portions of the program. Thank you very much for listening. I'm Brandon Rhodes.